In this video, let's take a look at finding the inverse Laplace transform of these four functions. First off, we have f of s equals e to the minus 4s over s to the fifth. So before starting this one, what happens if we ignore the exponential term in the numerator? We have the inverse Laplace transform of 1 over s to the fifth. Just for temporarily, let's forget about the exponential in the numerator. Well, if I do that, then I know that the inverse Laplace transform of this is going to be 1 over 24 times the inverse Laplace transform of 4 factorial over s to the fifth. And from the table, I know that the inverse Laplace transform of 4 factorial over s to the fifth is t to the fourth. And so the inverse Laplace transform of 1 over s to the fifth will therefore be 1/24 t to the fourth. So because I have this, I can therefore write the inverse Laplace transform of the original function very quickly. Everywhere I see a t, I'm going to replace by t minus 4. So 1 over 24, t minus 4 to the fourth power. And also I need to multiply by u sub 4 of t. And so that is the inverse Laplace transform of this function using the this first inverse Laplace transform that I used off the table. Okay, next let's take a look at the function g. S times this exponential over s squared plus 9. To do this, first again, let me take a look at the inverse Laplace transform of s over s squared plus 9, where I again drop the exponential in the numerator. Now from the table, I know that this is cosine 3t. And therefore, if I multiply this by e to the minus pi s, then the Laplace transform of this I'll get by everywhere I see a t, I'm going to replace by t minus pi. And also this has to get multiplied by the step function at pi. Now this can be simplified slightly using trig identities. I'm not going to make a big deal out of that for our class, but that's basically the answer. Okay, part 3. We have e to the minus s times over s squared plus 5s. Okay, so as we've been doing, let's figure out the inverse Laplace transform of 1 over s squared plus 5s. Okay, to do this, we've got a little bit of work to do first because we have to figure out the partial fraction decomposition. So I'll do that a little bit of work on the side here. We have 1 over s squared plus 5s is equal to a over s plus b over s plus 5. So 1 is equal to a times s plus 5 plus b times s. If I let s equal 0, then I get 1 is equal to 5 times a, so that a is equal to 1/5. And if I let s equal negative 5, I'll get 1 is equal to negative 5 times b, so that b is equal to negative 1/5. So using the partial fraction decomposition, this is 1/5 over s minus 1/5 over s plus 5. Okay, so running the inverse transform, this is 1/5 minus 1/5 e to the minus 5t using our table. So, to find the inverse Laplace transform of e to the minus s over s squared plus 5s, it's going to be essentially this function. Everywhere I see a t, I replace by t minus 1. And then this gets multiplied by the step function at position 1. And so that is the inverse Laplace transform for the function h. Okay, the last one's going to take a little bit more work. Laplace transform of 1 over s squared plus 4 quantity squared. All right, the first thing to think about is making the partial fraction decomposition. Unfortunately, that is the partial fraction decomposition. I have an irreducible quadratic squared. The numerator is linear, it's actually constant, and so that is the partial fraction decomposition. So the way that we're going to find the inverse transform is to write it like this. K of s is equal to 1 over s squared plus 4 times 1 over s squared plus 4. Now the inverse Laplace transform of 1 over s squared plus 4 is equal to 1/2 times the inverse Laplace transform of 2 over s squared plus 4. So that's 1/2 sine 2t. So this Laplace transform is the product of two things, and I know how to find the inverse transform of this, and I know how to find the inverse transform of this. Therefore, the inverse Laplace transform of k is going to be the convolution of these two functions, integral from 0 to t, 1/2 sine of 2u times 1/2 sine of 2 times t minus u du. And so I have this function twice, and I take the convolution of itself. And so then I have to figure out how to get this integral. Okay, now to get this integral, I'm going to use the hint that I see here, that the sine of alpha times sine of beta is 1/2 cosine of the difference of the angles minus the cosine of the sum of the angles. So 1/2, 1 times 1/2, so that comes out. There's also a 1/2 from the identity, which gives me a 1/8 out. Then using the identity, it's going to be cosine of the difference of the two angles minus the cosine of the sum of the two angles du. Okay, so I get 1/8 integral from 0 to t. Cosine of 4u minus 2t, integrating with respect to u. And this last part here, the 2u's actually cancel inside, and I'll end up with cosine of 2t, integrating with respect to u. Okay, so with that trig identity, I've changed the product of these two sines into the difference of two cosines, and I can now integrate both of those separately. So I get 1/8. Integral of cosine is sine. There's a 4u here, so I need an extra 1/4 out. Sine of 4u minus 2t. And I don't care about the 2t because when I'm integrating with respect to u, that's basically a constant. Minus, again, that is a constant with respect to u, so u times cosine of 2t, evaluated from u equals t to u equals 0. Okay, so plugging in the endpoints, we get 1/8. Plugging in t, I get 1/4. Sine of 4t minus 2t is 2t. Plugging in t, I get t cosine 2t. That's the first part. Plugging in 0, I get 1/4 sine of negative 2t, 0 minus 2t, minus 0. Okay, so 1/8. Okay, now here I have minus. This minus comes outside of sine because sine is an odd function. So these two combine, and I get 2/4 sine 2t minus t cosine 2t. And so the practical effect is I get 1/16 sine 2t minus t over 8 times the cosine of 2t. And that is going to be the Laplace transform of the function k. And so this one I got by setting this up as a convolution integral, using a trig identity, and then just integrating carefully to get the inverse Laplace transform.